again ask
in the
you for
last
the
week,
introduction. Yeah.
actually in the last week, we had an interview for till the Verilog. You told me you are going to take on Monday for the system Verilog and UVM.
Yes, yes.
On
Yeah.
Monday, actually, I was sick, so that's why I scheduled to Wednesday now.
Okay, okay. So yeah, I will again ask you for an introduction.
Okay, sure.
Yeah.
Uh, Thank you so much for giving me this opportunity to introduce myself again, ma'am. My name is Manoj Kumar. I'm from Andhra Pradesh. I completed my bachelor's in Vijayawada at KL University. There in the electronics and communication domain, I am specialized in VLSI, where we have this, our university provides the specialization. So we need to opt a specialization in order to get a degree certificate. So I opted the VLSI. There we learned about the low power techniques, low power design, VLSI design, what is VLSI, and also thereby my enthusiasm rise towards the VLSI and motivated it me to take uh, uh, motivated me to take uh, to complete the bridge gap between the theoretical and the company what we are doing, the real time hands on experience. So I opted the Mavan Silicon design verification course. Since why design verification? um, in my university they also trained me in, and I am very much familiar with the C language, so I do have the knowledge on the programming, so I choose design verification as my uh, career. So I learned about all the things from starting from the digital electronics to Verilog in Marvin Silicon. And coming to my hobbies, I'm very much interested in knowing about the new things, like the advancement of the semiconductor industry. And my short-term goal is to be get placed in a very reputed company where the work culture and the growth-oriented sector is there. Since I'm very much enthusiastic about VLSA, design verification field, so in that company there must be uh, like the knowledge exchange needs to be happen. And my long term goal is to be the uh, one of the finest design verification engineer in this world. That's all about me, ma'am. Thank you.
Oh, that's so nice. That was nice. Okay, so let's start the interview.
Okay.
So, what do you think that why we needed the system very long over very long?
In Verilog, there were different kinds of constraints, and we have the lot of limitations. In order to overcome those limitations, we are introduced with the system Verilog. For designing the modules, our Verilog is enough, and for some kind of uh, reusability and for that kind of thing, our system Verilog is very much needed. If we are comparing the data types, there is an enhancement in our data types and the interfaces is got introduced in system Verilog um, to overcome the burden are the signals interconnection errors. To reduce those signal interconnection errors, interface will be introduced in the system Verilog, and the powerful OOP concept got introduced in system Verilog. And again, and the randomization concept. In Verilog also we are having the random keyword and dollar u random and dollar random, but there is much advancement happened in system Verilog or the randomization through random. How we are going to control the randomization by using constraints, and how we are controlling the constraints and the randomization. These parts were introduced in system Verilog, and system where long language itself having the verification and not like verification system verilog assertions. By using system verilog assertions, we are going to validate the behavior of our design very easily. In order to catch the design bugs very quickly, we have the need of the system verilog language.
Okay, that's right. So, what are the two-state and four-state variable? Can you provide some
Yeah, ma'am.
examples?
Yeah, ma'am. Like if you are taking the reg variable, it can able to hold the reg data type can able to store the values of 0, 1, high impedance and unknown X and Z. And if we are coming we are coming to the two-state data type like bit. It can able to store 0 and 1. Here in system Verilog, the data types are four-state data type, two-state data type, struct, class, enum, and user-defined data types can be we can made by using the available data types. Uh, the, the, that is what the four-state data type and two-state data type map. Here in the system Verilog, we are got introduced with the logic. Logic is very similar with reg, but we are having the conflict. Like we need to use wire in the RHS side, and we need to use the reg module in the LHS side of our procedural block. So in order to overcome that procedural and that sequential and combinational issues, we got introduced with the logic. By using logic, we can use the data type in any of the procedural block or the continuous concurrent assignment as well.
Okay. So, mm, what are the X and Z values in that? What they
Uh,
mean?
there symbols like if you are passing the signal 1 and signal 0 to a single wire, then it is the unknown value X. And if it is high impedance means we are not providing the proper value. Like it can able to if you are providing 5 volts, so greater than 2.5 volts it will take as 1, and less than 2.5 volts it going to take the 0, it will consider in system. But if we are providing less than that of negative values, then it is the high impedance value.
Okay. So, what is the difference between the integer and int?
Yeah, ma'am. Here is two-state data type, and integer is a four-state data type, and integer is unsigned and int is signed.
Okay. Okay. So, like in Verilog, can I write like in a for loop, can I write int I equal to 0, colon
No,
some
ma'am.
condition?
In Verilog, it is not possible to declare a data type in the for loop. So it is possible in our system Verilog only. For int I is equal to 0, we can initialize like that. We can declare like this. But in Verilog, we need to declare out of the for loop integer I. Then we are going to give for I is equal to 0, I less than
So
something.
can I like declare it in the initial block?
Inside the initial block.
Yes.
Inside the initial block int I we can declare, ma'am. But if two initial blocks were executing parallelly and we are declaring in both the places I, then there will be a conflict. In order to avoid that conflict, we are using the begin block names, begin block 1 and begin block 2.
Yeah, actually we write like outside the initial generally. Um, so you know the randomization, right?
Yes, ma'am.
So why we need the randomization in system
Uh,
Verilog?
Randomization is needed to catch the bugs very early, ma'am. So randomization helps us to random the variables, like quality of the stim. So we can provide by using randomization. Like if you are having the variable of 32 bits, it is highly impossible. It will be possible, but it will be time taking process in order to generate those 32 values. But if you are using the randomization concept, we can randomly get the numbers, get the sequence of get the data item from the 32-bit sequence, and we can able to check like the bug is and in the range between from 2000 to 3000. If there is no concept of randomization, then we cannot directly provide the values. We need to do all the possible combinations. So here the randomization concept will helps us to provide the range like from 2000 to 3000. Then we can easily catch the bug and we can find what was the error in our RTL. and again we can recheck it.
Okay, fine. So you know how to write the constraints in randomization?
Yes, ma'am. Basically, these constraints are used to control the randomization. Or we can, if we wanted to generate that particular sequence, then these constraints are useful, ma'am. Mainly, these constraints are used to design the quality stimulus.
Okay. So we have a 3-bit random variable
Okay.
that
Like
values
you are sending in the chat or you are saying orally.
orally.
Okay, ma'am. I will take a note.
Yes. So you have a 3-bit random variable such that values 0 to 4 occur with 70% probability.
3-bit rand variable
Yes, such that the value 0 to 4 occur with
or occur with.
70% probability,
Okay, ma'am.
and values 5 to 7 occur with 30% probability.
Okay.
You know how to write the cover point?
Yes, ma'am, I know.
So you can also write a cover point to verify that all values are generated according to the defined distribution. Okay.
Okay, ma'am.
Okay.
Um, can I share this?
Yes, you can.
I'm using distribution constraint for this one.
I think you
Uh,
have missed some part.
yeah, ma'am.
You have
0
5
to
to
4
7.
values. Okay.
For the 5 to 7, yes, it's occur
Okay.
with 30%.
And you asked me to write the count point for this one, no?
Yes.
ma'am.
Yes, that's correct. So, okay, do you know what are assertions?
Yes, ma'am. Um, Assertions, um, system Verilog, assertions are embedded in the language itself in the system Verilog. These assertions are used to validate the behavior of our design. It gives the white box visibility to our black box design, and it provides the controllability and observability of our design. Like we don't know the RTL is like embedded, like it is that one we can't see inside what are the things happening in the RTL. So we can, by using this assertion, we can able to check what was the things happening. Like if the inputs and the outputs, we can able to find the bugs, whatever, what and all there in inputs and the outputs, but we can't able to find what are the bugs inside the circuit happenings. So that inside bugs can be identified by using assertions. Assertions increase the probability of finding bugs very easily, and and the assertions also having some limitations, like assertions we don't know the sufficient this much is enough for this design. And if you are writing any assertion is wrong, then it is very hard to debug. And there were the three types of assertions, mainly immediate assertion, deferred immediate assertion, and the concurrent assertions. Concurrent assertion supports both static and dynamic thing, and these concurrent assertions we are mostly preferring and using. And these concurrent assertions can be recognized by using the property keyword, and this is going to occur in the either positive edge or the negative edge. That's all about
Okay,
the.
okay, okay. So like you know no, how to write the assertions.
Yeah, ma'am, I know.
So I will give you a like question. You have to write an assertion for it, and can you explain me that only?
Okay.
Yeah. So you have a 4-bit counter. I'm like reading it orally.
4-bit counter. Okay.
Yes, which named CNT, CNNT.
These CNT are the signals, ma'am.
You have a 4-bit counter CNT which increments on every passage clock. No, CNT not. It's a CNT. It's joint. It's like a variable name. Okay. No, 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 no. C and N for you have to only write the C and N and T.
Okay, ma'am. C
Yes.
comma N comma T.
No, 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 no. It's joint. We
Okay,
have only
count
one signal.
CNT.
Yes, yes,
CNT
yes,
count.
yes.
Okay. Which increments on positive edge.
Yes, yes.
Okay.
When enable is high,
Okay.
so you have to write a assertion to check that the counter never exceeds 15. Okay? It should never exceed 15. You have to write an assertion only to check the if not exceed 15.
Oh, only for this one.
Yes, yes.
Okay. These are not required, ma'am. Assertions for counter.
These required, but I'm saying that you have to write an assertion to check whether the counter never exceeds 15.
Okay, ma'am.
Okay. You know FIFO, right?
Yes, ma'am, I know.
Okay, fine.
I'm completed. Here, um, I'm writing the concurrent assertions. Here I am checking for every positive edge of clock. Whenever there is a rise in the enable from 0 to 1, when there is a rise in enable signal, we are going to check in the same cycle itself whether the count is in between 0 to 15 cycles or not. If it exceeds, then it's going to assert, like the assertion is going to fail now. uh, from 0 to 15, it's going to be assertion is going to pass. That's it.
Okay, okay.
Here I am using the non-continuous repetition operator.
Which operator?
Non-continuous repetition operator.
Okay, okay. So what is the use of the dollar rows?
Dollar rows is going to check whether the enable signal is from 0 to 1 or not. It's going to check.
Okay, fine. Okay, fine, fine. So like I'm are you able to see my screen? I'm sharing my screen.
Yeah, ma'am, I will stop sharing.
Okay. Yeah. You have to give the output of this question.
Yeah, here we are controlling the constraints by using constraint mode. If you are providing the constraint mode of 0, the constraints won't work. If you are not, if you are providing constraint mode of 1, then it's going to work.
Okay.
By default, it is 1. And here in this code, we are having uh, 3 bit of variable x of data type bit. And here in the constraint, we are making, then it needs to generate in between 0, 1, 2, 3. Here while here our we are like construct after constructing the class into object, then we are randomizing. After randomization we are displaying the value must be in between 0, 1, 2, 3. Here it's going to display the first value is in
Okay.
between 0, 1, 2, 3, and after we are making the constraint mode 0, we are disabling the constraint, then we are randomizing. Now the object may be 0, 1, 2, 3, 2 to the power of 3. 200 to 2 to the 4 to the right. 8. From 0 to 7, the value might be any of the value. The second value.
Okay, so the first value will be between.
0, 1, 2, 3.
Okay, and the second value will be in between 0 to 7,
0
you
to
are
7.
saying. Yeah,
Yeah.
okay, fine, fine. It's correct. Okay, so like I'm giving you the next question. Wait, I think, yeah,
Got it. Module TP, task automatic counter, static in count is increment, dollar display count is equal to count and task repeat 3 counter 4 counter counter 2 times. Here we are using the automatic keyword. Automatic, by using this automatic keyword, we are going to generate the new memory. That
okay,
memory will be different for every time while we are calling the task. So in the first time, the repeat of 3 times. 3 times we are repeating. So our count will be 0 first, incrementing by 1, and the another time it is 2, another time it is 3. But here in the case of fork join, we are calling the counter 2 times. The counter value will be initialized to 0 and count increment 1, and again we are calling the counter, then it will be 1. First time we are using the repeat statement. In the automatic only we are going to be repeating for 3 times, so the count will be 3, ma'am. For the fork join counter, second time calling the task, it will be 1. Third time calling the task, it will be 1 only.
so what will be the like final output?
3 comma 1 comma 1, ma'am.
No, I don't think.
Like in the fork join counter 1, and again the counter will also be 1. In the repeat statement, we are calling the counter 3 times. So it also will be 1 only, ma'am. It won't increment. Like we are calling the counter first time, and it will be 1. It prints 1. Again, it's going to call. Again, 1. Again, it will call 1, triple 1. Then in the fork join, we are calling the two counters. Then this counter value also 1, this counter value also 1.
Okay, but
Five times.
on, like what will be the final answer, because it is not at 3, 4, and 5, I'm saying.
No, ma'am. 1 only. The final answer will be 1.
No.
Like the first repeat statement. First time the repeat statement, it will enter, ma'am, counter. Then it will print the count value equal to 1.
Yeah, repeat 3 means it will like repeat
Repeat for
many
3 times.
times.
The 3 times the dollar display value of count equal to means it will be 1 only, ma'am. Count is equal to 1, count is equal to 1, count is equal to 1. And in the fork join also, we are calling the counter concurrently. Then this value also 1, this value also 1 only, ma'am. Total five statements it going to print, and in the 5 statements, the count value will be 1 only.
No, no. You want to take time, or like can share you the answer?
According to my analysis, I get that answer only.
Okay.
Like if I am wrong, I will
So
uh,
yeah, so the
tell
answer will be like count equal to 1, count equal to 2, count equal to 3, count equal to 4, and count equal to 5. Because in a static int count, value is shared across all the calls of the task, right?
yes, but here it is automatic.
Yes.
So yeah, every time
Since the task is automatic, each call has its own stack frame, but the static variable is global within the task definition.
okay, ma'am. Okay, inside the static variable is there.
Yes.
Static in count equal. Oh, okay, ma'am.
Yeah. Do you know the difference between the fork join and fork join any and fork join none?
Yeah, ma'am. In the fork join, what are all the statements were there inside it, and it's going to execute concurrently, ma'am. In the fork join, any after executing the first task, like if our first thread is of working at 10 nanoseconds and the next thread is working at 30 nanoseconds, then the first thread which is working at 10 nanoseconds, after completing of the thread, it exits from the fork join any, and the remaining threads is going to execute according to their timestamps in the background now. In the fork join none, it just enters into the block, into the block, and it will exit, and the remaining threads what and all there, it's going to execute according to the timestamp in the background.
Okay. Can you share your screen like I am giving you a question on a chat box, like you have to paste it on your notepad or something you are using. Can you like paste it onto your notepad?
Yeah, ma'am. Sure.
It's
At
a
zero.
nested for fork join, yeah.
Okay, okay. Like the 0 units is the time simulation starts, ma'am. Like I'm considering the dollar time will be 0 nanoseconds. Now,
Okay.
I'm going to first execute this display statement, then it will enter this fork join. Since it is a fork join, it's going to execute all the threads inside it. There were three threads: begin end, and begin end. This flow must be in the sequential order. So first, in the first display statement of begin end, and this begin end and this begin end is concurrently triggered, and uh, first at 0 nanoseconds, outer block one starts, and also here the dollar display of 0 nanoseconds, outer block 2 starts, and of okay. Now in the fork join any means
Okay, you
like
said like
nanoseconds.
at zero
Yep, ma'am.
seconds, outer block one and outer block two will start.
Yes, ma'am.
Okay.
And these
And what
two,
about outer three block?
no, ma'am. And after 2 nanoseconds only, it's going to start.
Okay.
Here in the fork join any we are using 5 nanoseconds from 0 plus 5 nanoseconds. At 5 nanoseconds time, display of inner 1A done. It's going to print, ma'am. After 10 nanoseconds of time, here 3 nanoseconds, join none. Here this one is join none. At 0 nanoseconds, after join none, outer block 2 is going to print, ma'am.
Can you
Now, like I
write
will
it?
write at
Yeah,
last.
yeah.
Important I
Yes,
will.
yeah. Okay. Till the inner one you have said right. Till the inner one, A done block.
This fortune, the 2 nanoseconds. plus 4, 6, 9, 7. Okay.
Have you done?
Yeah, ma'am, done. Can I explain it, ma'am?
Yes, yes, you can.
Ma'am, in the zero simulation time, it's going to simulation starts and
Okay.
a fork join. the all three threads needs to be execute concurrently. Then in the begin end, it needs to execute sequentially. So first it start with the $display statement. Then it's going to print this one, and parallelly in this display statement also it prints at the zero simulation time. And after 2 nanoseconds, this statement is going to be printed. Zero, block one start, and block two starts.
Okay, okay.
Block two starts now. After 2 nanoseconds, this block three will going to start now. Like here, for join any. So any one of the statement is going to execute until hash 5. Here we are giving the delay hash 5. It is the minimum delay of this block. So it will wait till 5 nanoseconds. Till then this block will be idle. And
Okay.
in the for join none, uh, there is no criteria. Like whenever this display statement is printed, along with that, this display statement is also going to print. Uh, like in the 0 nanoseconds itself, this one is going to print.
Okay. At the
Uh, like after that, at 2 nanoseconds, the
Firstly, it was correct, but now it's not correct, I think. Previously, it was correct.
but here this was the fork join none. So whenever this will execute, okay. Since it was the begin end, it will block. Oh, after execution of this block only, this is going to print. Okay, my first I will explain.
Yeah, you can.
Then this
I
is,
think you like explaining the things and like teaching and all.
yeah, ma'am, actually I do these things a lot for my um,
Yeah, you explain everything to your friends, right?
um, but they are all placed.
Yeah, what?
But they are all placed, ma'am, except me.
Oh,
Mm. At 2 nanoseconds, this outer block three is going to print, ma'am. After two, this was the fork join block at four. Like this was the blocking. So 2 plus 4, 6. At 6, it's going to print the inner 3A done is going to print, ma'am. Then after already the 6 nanoseconds is done. So at 8 nanoseconds, this display of inner 3B is going to display. Then uh, after this 8 nanosecond, this after join is also joining outer block 3 is going to print the 8 nanoseconds itself.
I think inner three will print at 4 nanosecond. Yeah,
Oh, yes, ma'am. This one is printed in 4 nanoseconds only. It means already 2, 3.
you have written it at 10 nanosecond.
In 3B, 8
Sorry,
nanoseconds.
A1, A. Okay, so you have written it at 4 nanosecond. Okay, okay, right. Okay, okay, it's correct. And then inner A will run at 5 nanosecond. Yeah. Then the outer block, one of
Here,
the joiner.
inner A, this is going to execute at 5 nanoseconds, ma'am. Like this one 5 nanoseconds and this one 10 nanoseconds. Uh, um, After 5 nanoseconds, this one is going to execute since it was a join any block. At 5, outer block 1 is going to execute at 5. Block out. At 5 nanoseconds, this one is going to execute.
Yes.
So, other display. Here in this block will be at 0 nanoseconds. Outer block 2 is going to start. And after 3 nanoseconds, inner 2A is going to print. And at 7, inner 2B is going to print. But before that, before these two statements, after join, outer block 2 is going to print. Like this one at 0 nanoseconds. Outer block 2 start is going to print after join none. Outer block 2 is going to print, and at 3 nanoseconds, inner 2A done is going to print, and at 7 nanoseconds, inner 2B is going to print. And here, after 5 nanoseconds, inner 1A is going to print, and after that, after join any, outer block 1 is going to print, and at 10 nanoseconds, this display is going to print, and the uh, final simulation ended 10 nanoseconds.
Okay. So, like, can you like show me your answer also?
Okay.
But at 10 nanosecond, I think the for inner 1B,
Yeah,
it
ma'am, it's going to be in 10 nanoseconds.
yes, yes. Now it's correct. Yeah. So, have you done a MTech?
No, no, BTech. After that, I went for the training.
You are 2025 pass out.
No, ma'am, 2024 passed out.
Okay, okay.
So after
So
graduating
why
in
you have not like done the MTech or think of
like
it?
at that time I don't have any guidance. Like all of them were in the computer science itself. So lack of guidance, I went to the Marvin Silicon itself, like the training.
Okay. So
Like
now are you thinking like to give a gate and doing MTech? Are you thinking of it?
no, ma'am. Like first I wanted to get a job. After 2 years, I want to focus on the MTech. Like parallel, I wanted to do.
Okay.
Like economically
But I
also very.
think okay, but I think like you can give gate also. It will remain for 3 years. And if your plan change, like if you don't get any job, you can do MTech as well, side by side, till you get any job.
Yeah, ma'am, that
And
was a
from
good
the
idea.
college placement, you can also get a job.
Yeah, ma'am, I will try to give the gate. Like we need to prepare at least 3 months for that. So at this point of time, my whole
I think you
concentration on
can
getting a
do,
job, like
yeah.
mastering in UVM and system development.
Yeah, that's good. But I think your time will also save doing MTech and
Um, I will definitely think about it,
and
ma'am.
preparing for system Verilog and UVM. I think you will get some 1 to 2 hours for preparing for gate.
Oh,
Like it's a suggestion.
yeah, I will consider that suggestion. I will think about
Yeah.
it.
So what do you mean by the system Verilog interfaces
Ma'am, in Verilog, we are
and
connecting
why
two
like
nodes.
they're introduced?
In Verilog. We are connecting by using port or by name assignment or the order assignment. If you miss any of the assignment, if you like for 4 to 5 signals, it is easy for that. But if you are doing for thousand number of signals, it is uh, not. It is a tough task to connect to our DUT. So in system Verilog, they introduce the interfaces in order to avoid the cumbersome and the signal issues and also the challenges. In order to avoid those challenges, the interface got introduced. Interface is nothing but encapsulated bundle of signals. It consists all the signals, and interface can be synthesizable. And since in interfaces, interface consists of all the signal names and mod ports. We are particularly wanted to send
What
these
are the mode ports?
yeah, ma'am. Mod ports gives the direction to the subblocks. Like subblocks consists of top modules, some signals, and that signals input and output points are different when compared with the top module. Then we are using the mod port and to give the direction to our submodules. And also we
Like
are
what
having
they will get? Like they will suggest some modules that they are like input or output or something else.
yeah, ma'am. If we are considering a top block which consists of signal A and A, B, C. Here, A
Can
and
you
B,
like just draw or something to
yeah, here this one is our top module. No? Like these are the sub blocks which are inside our module. Like if you are having a signal A and that A is input to it and we're sending a back like this was B and B was output of our one block and input of our second block. And here the output will. So here B is acting like input and output. But
Okay,
we are declaring in the interface like logic and in the sub mod ports, mod port P1. Uh, in that we are providing input A, comma, output B for the P1 module. In the mod port,
okay,
we are providing B input B and C as output to the submodule 2. So here it is specifying the direction, whether the input or output. But it is different for the top modules in according to the top module and in accordance with the module 1 and module 2. So at that time we use the mod port in order to give the direction to our sub modules. And this interface is going to be synthesizable. Like if you want like RS-232 is the good example for our interface. An interface consists of clocking blocks. These clocking blocks is used to avoid the race condition for our test bench and DUT. If you are like I say, it is synthesizable one, so it is a static component interface. In order to connect the static component with our dynamic environment of test bench, we are using this interface reference. So the virtual interface we are using here. That is about the interfaces.
okay. So why UVM is required?
Uh, UVM is a framework, ma'am. It is a methodology. Like here in the system Verilog, the
What do you mean
challenges.
by the methodology? Like,
Uh, it is a framework which is built on system Verilog, ma'am. Like the developers already developed that framework, ma'am. So we are
okay,
using the developed framework by extending the classes. So here in reusability and portability in the plug and play manner is not possible in system Verilog, but it is possible in our UVM. And uh, controlling the number of object creations from the top block itself is not possible in system Verilog. That is possible in UVM. And also there is no proper communication. The language interface is also an issue, ma'am. Like if you are using the mod port, that mod port is available in the system Verilog classes only, in the system Verilog environment only. If you wanted to communicate with the other language like system C or the C test pages, it is not possible in system Verilog. But by using the TLM 1.0 and TLM 2.0 ports and analysis ports, we can able to communicate with the interoperability. That interoperability UVM providing now. And also it having a dedicated sequences and sequence item. Thereby, test case writers can develop their own test cases and send it to
So
our
how we can connect the sequence and driver using the sequencer?
sequence and driver. Yeah, ma'am.
No,
Sequence
I'm
and
saying
directory.
that how to connect the sequence and driver using a sequencer.
By using TLM ports, ma'am.
Okay. Like, can you code something for it
Yeah, ma'am.
if you know?
Yeah, ma'am.
And what do you mean by the TLM?
Transaction level modeling, ma'am. In the connect phase, we are going to connect like this is how we connect the driver and the sequencer now.
So
Uh,
what is TLM here?
like this sequence item port and
Okay.
sequence item export are the TLM ports and exports.
Okay.
Here, the TLM 2.0 having for one-to-one communication, we are having UVM TLM port, UVM TLM implementation, and UVM TLM get port, UVM TLM put port, and UVM TLM get implementation, UVM TLM um, get implementation put implementation and get implementation over there, ma'am. So thereby the one-to-one communication, if it is acting like a initiator and the target, then it these TLM points will manage, ma'am. If our both components is acting like the initiators, then there is a requirement of our FIFO. That FIFO consists exports, ma'am. UVM TLM export, and the implementation is already inside the FIFO. So it having export ports, and for one-to-one communication, it's okay, ma'am. For one-to-many communication, we got introduced with the analysis ports, and analysis port has inbuilt function. It is write function, ma'am, and it having port and export. By using port and export, we are going to send our transaction to the scoreboard or the subscriber, whatever the component it is. That is about the TLM.
Hello. Yes.
Yeah,
So like how we override a component using a factory?
yeah, ma'am. Factory is used to manufacture the UVM components and object classes, ma'am. Factory provides the overriding. Um, Like we can
English should be
override by
also.
using global override and the instance override. Only overriding, ma'am, registering also.
Only overriding.
Yeah, ma'am. Ma'am, here, if you are using this method, set type override by type, inside the build phase, we are mostly using overriding concepts. And by using this method, we are going to change the transaction one class into transaction two class. Wherever inside our environment, wherever the transaction one class is there, that is overridden with our transaction two. And in the instance override, we are providing the path. Only the driver, uh, agent zero's driver is going to be changed its transaction from transaction two to transaction one to transaction two. That's it. And the significance of replace is here at one time we are changing. If you wanted to change another time, then the bit replace needs to be one. By default, it is one. So if it is one, then we can change numerous times. Ma'am, ma'am, you are not audible actually. Like you asked me the global override and instance override. This is. Can I explain it another time, ma'am? No, ma'am. No, ma'am. This sequence to start of sequencer. And sequencer, M sequencer, it's pointing to sequencer. No, that sequence, we don't know which agent sequencer we are pointing here. So we need to provide environment handle dot what was the agent, either agent 0 or agent 1 sequencer. Yeah, ma'am. Here we are not providing uh, which sequencer. So it don't know, it won't work, ma'am. It don't, it will throw some error. From here, this sequencer, the start methods have UVM sequencer base. Sequencer is equal to, we are providing that sequencer here. That is directly pointing to the M sequencer. But here we are providing handle only. And that handle has which sequencer we are providing. We, uh, we are not defining the particular sequencer here. So, um, uh, it it won't work, ma'am. Okay, ma'am. Okay, ma'am. Here, um, the main aim of objections is to block that phase till it drops the objection. So, the sequence till the completion of this sequence driving to our sequencer, this phase is going to be blocked now, and our simulator is going to raise the objections and drop the objections. If the rising and dropping the objections count is equal, then only we are proceeding to the extract phase. So, if we are not providing the drop objection, we are just raising the objections itself, then it the count mismatch happens and it will wait for 9,200 seconds and then it exits from the simulation. That's it. Like we can raise the objections after the rising also. We are having the final thing like phase ready to end. In that area, we can raise the objections. That is the last way to raise the objection. That's Here we are using the concept of virtual sequence and virtual sequencer. And here the virtual sequencer having the handles of physical sequencers. Uh, Virtual sequencer having the handles of our physical sequencer. And inside the virtual sequence, in the virtual sequence, we have the handles of virtual sequencer and physical sequencers. Along with that, our sequence is also there. Now send we are going to send our sequence 1 and sequence 2 to um, to the sequencers, like what and all the handles which were there inside the virtual sequence we are sending them. So, and that will be assigned to our virtual sequencers, physical sequencers. So it will be connected from a virtual sequence to our physical sequencers. So basically, this virtual sequence and virtual sequencer concept is introduced to avoid the path dependency. Here, the path dependency is there. In order to avoid this path dependency, we are introduced, and virtual sequence is used in order to increase the reusability. Yeah, ma'am. I give an interview for the Altera and MediaTek. So till the last rounds I went in the Altera. In the CDC concept, I failed. I failed in that CDC concepts, so they rejected. And for MediaTek, I went 1 hour, 1.5 hour late. So they took the interview. It went well, but after that, I don't got any call from them. Like for MediaTek, it was the consultancy, ma'am. For Altera, it's for only the internship for 12-month internship. Uh, it was from the Maven Silicon itself. No, ma'am, I'm just mentioning the connections itself. I'm just making the connections itself. So, uh, can I create the memory also, ma'am? I created the memory as well. Like the most of the connections, like the sequence connections and the sequencer connections and the virtual sequence memory allocation, these all happens inside the virtual sequence task body, and we are extending the virtual sequence and creating a new class like sequence one. In the sequence one, we are directly starting the sequence one to sequencer one, and in the sequence two, we are starting to the sequencer two itself. The whole thing I am writing inside the single task body itself. That's it. Hyderabad, in my home itself. Uh, which thing, ma'am? No, ma'am, most of the companies in the Bangalore itself. So in Hyderabad, the tech giants were there, like Cadence and Nvidia, those kind of. I okay, ma'am. I don't know. I am not familiar with the yes, ma'am. AMD Mastership. Like without refer, we can't go to AMD and Mastership. Okay, ma'am. Like ma'am, when the referring of candidates will happen, like after completing these mock interviews. Like I enrolled for the premium referral program.